So it's
Yes.
okay.
Okay, Kedar, just 1 second.
Yeah.
Kedar,
Yeah,
wait.
so let me just, Rajiv, you want to
So
sort of
welcome everybody to the last day of the QMAT 2021. This is the morning session. The session chair will be Professor Krishnendu Sengupta from IISER Kolkata. And just a few announcements. The talks will be 25 minutes plus 5 minutes question and answer. We will relegate the questions to the end of the talk. If you have a very pressing question, you can type it in the chat and the chair will take it up at the appropriate moment. And there will be some breakout rooms if you have some discussions that are going on which is not resolved immediately. We would urge you to use the breakout rooms so that the other talks can go on in this session without interruption. And with that, let me hand it over to Krishnendu to conduct this session. Krishnan.
Okay, thank you, Rajiv. So, Kedar, I'll probably give you a hint at around 22 minutes. And
Yeah,
then,
that would be very useful. I've tried to keep it brief, but do give me warning.
Sure.
Yeah.
Okay, so let's start. So the first talk of this session is by Professor Kedar Damle from TIFR. And he's going to talk about emergent moments and random singlet susceptibility of a SU2 symmetric Majorana spin liquid. So, Kedar, over to you.
Yeah, so I'd like to begin, of course, by thanking the organizers for this invitation and for Krishnendu to make it to his office this early. My apologies. But I hope it will be worth it. So what I want to describe is an interesting, exactly solvable example that puts a little bit of flesh on some phenomenological ideas that have been very popular over the last 2 or 3 years, I think. But let me go back many decades ago, actually, not 2 or 3 years ago, to begin with, to provide some background. And the background is the random singlet physics of phosphorus doped silicon, which came into prominence in the 70s when people started intentionally doping a silicon matrix with a very small density of phosphorus. Phosphorus basically can be thought of each phosphorus atom can be really thought of as a site of a half-filled Hubbard model on this random lattice because of its electronic structure. And so at very low energies, what you really got is you got the physics of spin half moments that live on each phosphorus atom. There's one dangling spin, there's one electron that's localized in a big orbital around the phosphorus. And the question is, how do these spins interact in the inert silicon matrix? And there was a lot of data, and that's what sparked this theoretical investigation by Bhatt and Lee. And they came up with this very nice picture. They said, imagine that there's these exchange couplings between the spins, which are antiferromagnetic, but distributed very widely in magnitude because the distances between the pairs are very widely separated, right? And variable. So they said, well, one way to think about susceptibility is to sort of imagine doing a renormalization group approach, which they actually implemented, but the argument can be made without the implementation. So imagine you run some renormalization group approach where you freeze successively pairs that have a large binding energy into singlets, and you lower the cutoff to sort of the level of the temperature. So you look in the renormalized problem where the cutoff of the largest renormalized J is T, and then you argue that the distributions of couplings and in that renormalized problem are so broad that in that renormalized problem, whatever degrees of freedom are left behind, you can simply think of them as free spins that respond with a Curie tail to the external magnetic field. And so this will give you a susceptibility, which is simply 1 over temperature, which is the Curie tail, times the number of degrees of freedom, N of T, that survive up to an energy scale T in this way of doing the renormalization. And what they discovered is that this N of T by T behaves like T to some alpha minus 1. Alpha is not exactly constant, but it's approximately constant. So it's some sort of effective exponent, which varies very slowly with temperature in the range 0 to 1. Right? So this was their phenomenology. This came to be known as the Bhatt-Lee phase or the Bhatt-Lee phenomenology or the random singlet picture. One less emphasized aspect of this in the original literature is that this way of thinking also tells you what's the dynamic susceptibility at a low frequency. at least when the low frequency is higher than the temperature at which you're making the measurement. And this is something we pointed out some 2 decades ago. And the idea is that you run this renormalization group again up to the scale, and then you ask what fraction of the couplings are at the cutoff, right? And if you think about it, those are the couplings that will get decimated at the next step in the RG. So, and each one of those couplings corresponds to a pair of energy levels in the many body problem at exactly the frequency omega which you're measuring. So it will contribute to chi double prime of omega. So in other words, chi double prime of omega in systems like these are just, it just measures the d and d omega. It just measures how the degrees of freedom are changing with cutoff. In some sense, it's a density of states in this precise sense, right? So this is background. So with these 2 pieces of information, you can define a diagnostic of disorder strength. By strength, I mean how broad are the distributions in the effective low energy theory. And this is simply the ratio of n over omega to d and d omega, right? And what it's really doing, is the inverse of delta. If you think about it, is the same as chi double prime of omega divided by chi at a temperature, the thermodynamic susceptibility, but measured at the temperature T equal to omega, right? So what is this inverse, delta inverse? It's basically measuring the renormalized disorder strength. It's measuring how broad your distributions are. The bigger the delta, the broader the distribution, right? Because delta inverse will go to 0 if the distribution is very broad. So since this natural measure of the width of the distributions in the renormalized problem has a logarithmic derivative here in the denominator, a natural variable to look at everything in is the log. So you look at log of the current energy cutoff or the frequency of interest, and you take the, so log of omega naught, which is the overall cutoff, divided by the current cutoff of the frequency of interest. That's what you call gamma. And so Bhatt and Lee's claim was n of gamma. You can now ask how many degrees of freedom are left at frequency omega, convert it to a gamma, and then n of gamma is exponential minus alpha times gamma, where alpha is slowly varying with gamma. And then you can rewrite everything in terms of derivatives with respect to gamma. The point to remember is that if alpha is tiny, which is if it's 1 over z and z is a constant, that's finite but strong disorder. That's what we call a Griffith's phase. Okay, this is all just phenomenology, no calculation here. So the first precise calculation that put flesh on all this was on a one-dimensional antiferromagnetic exchange model, first by Dasgupta and Ma, and then by Daniel Fisher, who sort of really pinned it down analytically. And it showed that in this problem, without getting into the details, the distributions broaden as log of the cutoff, log of omega naught by omega. So as you go to lower and lower energies, the effective width of the distribution is getting bigger and bigger, but logarithmic. And this n of gamma, which is the number of degrees of freedom left behind, is 1 over gamma square. And this leads to an almost Curie response of the 1D chain. In 2 or 3 dimensions, when you ask for the same questions, and this was done both by Bhatt and Lee originally and by Motronic and Hughes in 99, that's unpublished, it was found that the distributions do broaden, but not indefinitely. And so the ultimate low energy physics is not completely clear. So that was the status of this phenomenology in higher dimensions until recently. And more recently, over the last 3 years, there's been a lot of sort of interest in using this kind of description for a very wide variety of systems. And I'm not an expert on these systems per se. They are complicated, frustrated magnets. Some of them have bond disordered phases. Some of them look like a nematic. But the point is, all of them seem to have a susceptibility, a low temperature susceptibility, which at least phenomenologically fits this picture. And this way of thinking was advocated in bond disordered valence bond solid phases proximate to spin liquids by Kimchi, Nahum, and Senthil. And I think that's partly what started all this. And they were themselves motivated by particular experiments on this compound. And then Sandvik and his group produced numerical evidence that this indeed happens in some controlled calculations. And there's other work that extends this kind of phenomenology to systems with a small amount of spin orbit coupling as well. And what they claim in this generalized way of thinking is that in many, many systems, even if the distributions don't broaden indefinitely, and these are many, many systems in 2 dimensions, frustrated magnets, you get behavior that looks like random singlet. modified slightly by spin-orbit coupling, but you also get a Curie tail. So it's almost as if some degrees of freedom freeze out as you lower the temperature, but there's always some dangling spins left that give a Curie tail even at the lowest temperature. So this is the phenomenology. And I think I've used up half my time roughly, which is good because this is important. And so now with this background, I want to show you that one can do a simple, simple in the sense well-defined at least calculation without invoking all these sort of phenomenological ideas whose status we don't know, right? In this calculation, we take a tractable, exactly solved model of an SU2 symmetric Majorana spin liquid. The model is not invented by us; it's been around for 15 years. But we have noted in our work recently that it has a susceptibility which you can actually calculate, partly analytically and partly by precise numerics which are controlled. It has a susceptibility that is exactly of this form. It has a Curie tail term. These you should think of as spins that remain free all the way down to 0 temperature. And then it has exactly this random singlet phenomenology, t to the power alpha minus 1 with some slowly varying alpha as temperature goes to 0. So like I said, C is the density. The Curie tail comes from emergent magnetic moments, which remain free all the way down to 0 temperature. And the point is, these are not the original microscopic spins. If you ask for the form factor or the wave function of these moments that are giving you this Curie tail, that form factor at low dilution or low disorder is actually very big. It's spread out over many, many sites. So this is a collective effect, this Curie tail. It's not a trivial effect having to come with single dangling spins, right? It doesn't have to do with that. And the point is alpha of T is indeed controlled by a strong disorder fixed point. So this is really a proof of principle calculation that says everything people have been talking about over the last 3 years does happen at least in one controlled example. And so this leads to a very natural question. Our calculation doesn't work in this Bhattli way of renormalizing down the couplings. It's actually a direct calculation based on the fact that this is mappable to free Majorana fermions with some static gauge fluxes. So if that's the case, is there actual picture in terms of freezing pairs of singlets? And I believe yes, but that picture has not yet been converted into an actual calculation by anybody. So actual calculation proceeds via Majorana modes and exact solvability, but the picture is identical to the Bhattli one. So the setting is the honeycomb model of Yao and Lee, which is a kind of a souped up Kitaev model where think of the tau variables as orbital degrees of freedom. And the spin variables, the S variables are spin degrees of freedom. So there's a S dot S Heisenberg interaction between nearest neighbors on a honeycomb lattice, but its strength is not a constant. It's a dynamical variable itself, and it's given by tau lambda, which is the product of the orbital Pauli matrices of index lambda, where lambda is the orientation of the honeycomb lattice bond, exactly like in the Kitaev model. So if you drop this S dot S multiplier, what you would get here, tau lambda, that would be the original Kitaev model. So what you're doing is on every bond operator of the Kitaev model, tau lambda, you're multiplying it by S dot S, where S is an actual spin half variable, right? Which has full SU2 symmetry. So this is an odd model. But Yao and Lee pointed out that it's exactly solvable, and it does have some physical interpretation in terms of orbital degrees of freedom and spin degrees of freedom. You can start with a spin half antiferromagnet on the decorated honeycomb lattice, and the low energy physics in a certain limit will be exactly this. And this has an exact solution using Deeptiman Sen and Sriram Shastri's Majorana representation. I should say the Shastri Sen Coleman Mirinda Swellick representation. Where you write sigma z as minus I sigma cx cy and tau z as minus I bx by, and cyclically all the other ones as well. So I won't belabor these calculational details because this is fairly standard by now. Once you plug this in and you use the constraint, you realize that the things break up into two sectors. There are two faithful copies of the physics. You can pick any one of them by this projection operator. And in the sector you project to, bilinears of sigma and tau reduced to bilinears of C and B Majorana operators, which makes it exactly solvable. And so in effect, you get three copies of Kitaev's non-interacting Majorana model, all coupled to the same gauge field. So that's what the Hamiltonian looks like. And then the susceptibility that I'm interested in just becomes the compressibility of these fermions at half filling, right, in a particle hole symmetric hopping problem. And so this is, of course, modulo projections, but as Matthias Wojta and Shosky have shown us, for specific boundary conditions, the subleading corrections coming from projections are actually zero, so you don't have to worry about them even. And so this is the calculation we do. We basically have to look at the spectrum of free Majorana fermions on a disordered honeycomb lattice, which has both vacancy impurities and bond impurities. And we have to ask what the density of states looks like, because that's what controls the compressibility. And we have to ask whether it's controlled by one of these strong disorder fixed points, which has its signature in the form of the density of states. So if it looked like the one-dimensional chain example, then dn d omega should be some power law in omega. If it looked like a two-dimensional bipartite random hopping problem, then you should get n of omega going as gamma to some power e to the minus something, which is a stretched exponential form. So basically you have to ask whether it looks like a stretched exponential or a power law, n of gamma, and that's what we did. And here, the motivation was that in the regular Kitaev model, Valence, Chocker, and Mosner had already looked at it and found some anomalously power law-like behavior, which you don't expect in 2 dimensions, because that's the one-dimensional sort of physics of random singlet behavior. And so they left it at that. And then in closely related problems having to do with graphene with vacancies, this was converted to a claim about a new universality class. Which turned out to be false, actually, as we showed some years ago in the graphene problem. What happens is that there is a very long crossover where the physics looks like it's one-dimensional, and then it goes over to the two-dimensional random hopping form. And we found the same thing in the Kitaev problem as well more recently. And that's this is n of gamma versus gamma, and you can see that it's a power law up to a point, and then at lower energies it bends down, which is the stretched exponential. So this is all good, but here's the surprise. There's also a generic density of zero energy modes, exact zero energy modes, which are topologically protected. This we had noticed in the graphene problem as well, and now we find them in the Kitaev problem as well, and that's not surprising because they're topologically robust. So this was the old graphene result for how, the density of these zero modes, and the Kitaev problem gives basically the same thing, very similar. That's what we find recently. And these zero modes are the ones that give rise to this Curie tail in the susceptibility. So that is the basic message. And if you look at the wave function of these zero modes, you find that they don't live on just 2 or 3 sites, which would correspond to just a dangling spin in the spin language. They are spread out in space over very large regions at low dilution, at low vacancy concentration. And they really represent somehow a collective effect where there's a spin texture that forms because of the disorder. And the spin texture is organized in such a way that it remains, it's able to behave like a free spin all the way down to zero temperature. And surrounding it, there are singlets that form, and you get the random singlet part, and you get this Curie tail from this texture. So that's basically the picture. That there's a large length scale cooperative effect that controls the Curie coefficient, and we can characterize it very precisely. So with that, I'm going to stop on the dot so that there's time for questions. So the work on diluted graphene was by Sambuddha Sanyal, who played the key role, and we had a lot of help from Leszek Motronik because his thesis work also had involved similar problems 20 years ago when he worked with me. For the SU2 symmetric Kitaev work, again, it's Sambuddha Sanyal who did all the heavy lifting. And we got in touch with and collaborated with John Chocker and Roderick Messner because we were revisiting their old calculations that motivated everything. And for the fact that these zero modes are spread out over these large length scales and have interesting structure of their own, and they're a collective effect, that has been explored in some detail by Ritesh Bhola and Shaunak Biswas and Mursaleen Islam. And all of this was seeded by an Oxford India travel grant, which allowed John Chocker to visit me. And the work at TIFR, of course, we are very grateful to DAE and to SERB and the Infosys Chandrasekharan Center for funding it. Thank you. So let me stop here and
Okay.
take questions.
Okay, thank you, Kedar, for a great talk and for finishing early. So we have time for quite a few questions. So please go ahead. Whoever has this, just unmute yourself and ask.
Okay, can I ask with a vague question then?
Sure.
Okay, so
That's why I left a lot of time. I have other things to say, but I thought it's better to see what the questions are.
Okay, so in this problem of yours, is there a way to, I mean, in some clever way, just directly access the zero modes or write some clever basis for the zero modes?
Yeah, very good. So no, we don't have a, well, we can construct some zero modes by hand. That's not hard. It's just a matter of sitting down with a piece of paper and doodling. And that's how all this started, actually, when I kept doodling compulsively for many, many months. But I think the more interesting question, which is basically what you're asking, but let me rephrase it, is to ask what I kind of alluded to. Are my slides still visible?
Yes.
Yeah.
Good. They are small but visible, right?
Mm-hmm.
Yes. Yeah. So this is the real question. Is there, can you really come up with a way in which you take the Kitaev-like model of Yao and Lee and start making singlets, right? And in that way of thinking, can you understand why there are some degrees of freedom spread out over large regions that never form a singlet? That is the real question, I think, right? And if one could come up with at least an approximate understanding of that, it would free you from this constraint of exact solvability. And you might really understand what's going on, even when when various people say that the experiments fit this phenomenology. Right. So let me just offer one observation. We have not managed to do that. If we had, I would have given that talk and not this. That would have been infinitely more exciting. But let me offer one observation, and maybe you can also think about it. You see, if you take the Hamiltonian, you've got S dot S, but what's multiplying it is a bond that fluctuates. That's one way to think of it, right? The bond itself, the bond magnitude J is an operator. It fluctuates. It's actually tau lambda, tau lambda. So you could ask if you had, and there's of course the actual magnitude of it, which I've just kept out as J in this simple way of thinking, but there's actually a J lambda, tau lambda, S dot S. So imagine you have a system where the J lambdas have some disorder and you pick the largest magnitude. Now, the first thing you might immediately object to is, wait a minute, J lambda usually we say is antiferromagnetic, and that's why there are singlets being formed, and that's why there's a random singlet description. But here J lambda is getting multiplied by a dynamical variable tau lambda. So how can you even say there are singlets, right? Because sometimes you might be in an eigenstate of the taus, so that tau lambda is -1. And so then you'll have minus J lambda S dot S. Right? Let's say all the J lambdas are positive. Then you will have minus J lambda S dot S. If tau lambda are in an eigenstate where they are -1, right? So that's a ferromagnet. At least that bond is a ferromagnet. What singlets are you talking about, right? So you could worry about that. So this bothered me for a while, and it actually has a very simple and I think instructive answer. And it goes back to an observation of Deepak's from, I don't know, 15 years ago. Deepak likes to say when he teaches StatMech that the ferromagnetic coupling is more frustrated than the antiferromagnetic coupling. And what does he mean by that? He just means you take S dot S and diagonalize it. You get +1/4 and -3/4, right? So if you have a plus sign in front of the whole thing, the ground state energy is -3/4. If you have a minus sign in front of the whole thing, the ground state energy is -1/4, not -3/4. It's higher. And so this sounds like a trivial and useless observation, but in this problem, this is the key. You see, if you have tau lambda multiplied by a very large J, no matter what its sign is of J, what will you freeze the tau lambda into to minimize the energy of this bond? Well, always into such a eigenstate that the product of J times tau lambda is positive. So you'll always make an antiferromagnetic coupling for the S. And I think this is the key point about this system. And somehow this has to get incorporated into a renormalization group description. And I've not been able to do it. I struggled for, I don't know, 6 months, 8 months, but I've not been able to do it. But it's very cute. And I think it should be possible. I'm just not being clever enough. And that would be the right way to think, because then you would be freed from any constraints of solvability. Okay.
Yeah. Okay.
Okay. Other questions?
Yeah. Hello. Am I audible?
Yeah.
Okay. So yeah, maybe a very naive question. So my understanding is that so you are, I mean, in this random spin singlet. So the state is like that, is that you have a kind of quantum spin liquid, but where the J's are being distributed, right? Or you have a valence bond solid and your J's are distributed.
So the way you should think of the random singlet state is think of it as a valence bond glass with a broad distribution of valence bond binding energies. It's a valence bond glass. If you want to characterize its spatial structure, it's a valence bond glass. Right?
So yeah,
but the random singlet aspect of it is that this valence bond glass, well, valence bonds are not just lines you draw. There's also an energy scale associated with each line, right? So that bond energy, that energy scale is distributed very widely all over. From the cutoff down to the lowest energy, there's a broad distribution. So that's a valence bond glass. That's the random singlet.
So yeah, maybe one more related question. So my point is that how, as you told that from susceptibility, one can distinguish these states with respect to a normal spin liquid or other states. But how about the excitations? So will it be different with respect to any other conventional valence bond solid or quantum spin liquid type of state?
So valence bond solids also have conventional triplet excitations. This also has conventional triplet excitations. The point is that the spectral function of the triplet excitations looks very different. And that's exactly the point here. That's exactly the point here. I mean, in effect, you can measure the spectral function of the triplet excitations here, right? Chi double prime omega, I've just said, is d and d omega. So the form of the spectral function of the triplet excitations is very different. It has singular behavior at low energy. That's what characterizes the random singlet state. Because remember, d and d omega is 1 over gamma cubed or something like that in the 1D chain. And gamma is log of the energy.
Okay, thank you very much. Thank you.
Okay, I think we are exactly on time.
Yeah. So thank you, Kedar. So maybe if you have, if anybody else has other question, you could just could go to the breakout room.
Yeah, I'll go there. Yeah. Great.
And,
thank you.
Maybe, thanks, Kedar. Very nice talk. Yeah. Okay, so the next talk is by Sanjeev. Sanjeev, if you can share your screen. Sanjeev, can you please share your screen?
Yes, I am doing that.
Yeah, okay.
Let me go to the first page and.
Yeah, okay.
Right.
Play.
Yeah.
Great. So, okay, so the next talk is by Professor Sanjeev Kumar, and he's going to talk about skyrmions and antiferromagnetic skyrmions in spin orbit coupled Hund's model. So, Sanjeev, maybe after 22 minutes, I'm going to just sort of give you a heads up and then.
Perfect. Yeah.
So 25 for the talk and 5 for questions. So
sure.
Okay.
Yeah.
Okay.
Okay, thank you, Krishnendu. And I would like to start by thanking the organizers, for this kind invitation to present some of our works here. And the plan for today's talk is to. Am I audible? Because
yes,
yeah.
Okay.
Sure,
some noise in between. Yeah. All right. Yeah. So the plan is to present the work that 2 of my recently graduated PhD students have done, and it's sort of listed over here in these papers. Of course, I will not try to attempt and cover everything, but I'll essentially try to pick out some important aspects from this work and present that here. And so let's get started. Oops. Yeah. So here is the outline of the talk. So I'll begin by basically giving a brief introduction to what magnetic skyrmions, anti-skyrmions, and antiferromagnetic skyrmions are, and what are essentially the ways they are observed in experiments, and how theorists have tried to understand these textures or their formation. Then, I will sort of go on to my topic, which is trying to understand all of these in a framework which involves treating the electronic degree of freedom explicitly. So you look at a model which retains the electronic degree of freedom in it, and you try to understand all of this from there. And so I'll try to discuss cases for metals as well as insulators if time permits. Otherwise we can also stop at any stage. That should be fine. And finally, I'll conclude. So let me begin with the introduction of skyrmions. So here, this is what I call just a visual introduction to skyrmions. So the idea is these textures that are visible on the screen, these have been given these different names, and the point is that if you have a ferromagnet, and so these excitations, which apparently are topologically stable, can appear in certain magnets, and they can be characterized by the way these variations of the magnetic moments are shown here. So if you look at this picture A, this would be called a Neil skyrmion, where so imagine everything else is up spin far away, and here is a core of this skyrmion which has a down spin, and then this spin tilts outwards to the upspin in this fashion. Now there are different possibilities for this spin to tilt out in terms of this pattern formation, and that's how one comes up with these names, sort of Neil skyrmions or block skyrmions or anti-skyrmions. And of course, there is a way of mathematically precisely defining all of this in terms of this what one calls topological charge. So you can calculate this topological charge, which is an integral over over sort of this combination of the spin field, and then you get an integer for it if you have a perfect skyrmion, anti-skyrmion, or sort of formation of these objects. These objects have kind of become more important or relevant for the community because of this proposal of using these in the racetrack memory devices as sort of ways of storing information or manipulating information. And in that context, it turns out that skyrmions actually suffer from what is known as the skyrmion Hall effect, which means if one tries to drive these objects along these race tracks, then they have the tendency of getting deflected to the side via what one calls Magnus force. And a way to cure that problem is to come up with some variants of these, which are known as antiferromagnetic skyrmions. And this is a picture shown over here. So the idea is that you think of two sublattices and imagine a skyrmion living on each of those sublattices, and then you kind of merge these two pictures together, okay? Intertwine these two pictures. And the resulting object is an antiferromagnetic skyrmion. And it turns out that if you run this antiferromagnetic skyrmion along the race tracks, they have much less tendency of getting deflected to the sides. And so these are the papers which you can kind of look at if you are interested in a broad overview of these topics and a detailed introduction to these ideas. So let's now move on, and I'll just briefly tell how experimentalists detect these. So the main techniques that are used for detecting these is one of them is what we know as spin polarized STM. So you perform an STM experiment, but somehow retain the information about the spin direction by polarizing your tip in a certain way, and then you can actually map out the magnetic pattern on the surface of the material. Of course, this is essentially a surface technique. And this is an example from this paper where you have iron multilayers grown on iridium substrates, and you can actually back calculate in some sense the directions of magnetization and how they are arranged on the lattice in some sense. And here what one sees in this picture is an example of a skyrmion lattice. Well, in some sense, it is not one has to sort of do an extrapolation to call it a skyrmion, because we don't have this perfect mathematical description here, because this pattern is being sort of visible over only few lattice sites, in the sense that this can be seen as a sampling from a continuum configuration or on the lattice points, right? So given that extrapolation, one can call this a skyrmion lattice. The other technique that is commonly used to detect skyrmion textures is Lorentz transmission electron microscopy, and these are some of the pictures from LTEM. And of course, if there is a lattice formation of any kind, then you can go and look at the neutron scattering experiments, and you would see this pattern of multiple peaks due to, or the sort of the description of the lattice would be present in terms of these sans sort of scans. And one would think that they are rare sort of textures to find, but it turns out that they are not so rare anymore. And this is a review from this year, which essentially lists the materials which have been identified as skyrmion or anti-skyrmion materials, and various details are provided in this table, like what are the transition temperatures, what are the sizes of the skyrmions that are formed in these materials, what is the type of the texture, for example, is it block type, is it nail type, is it anti-skyrmion, and so on. And also their conductivity, like these are metals or insulators. And of course, there is an attempt to label a mechanism in some sense. So this is a very nice, comprehensive sort of list that is available with us now. So if you talk about a possible way of understanding skyrmion formation, you can kind of divide the efforts into two parts. One you can call continuum-based models, and this is essentially what one starts with. So I think the first paper which kind of showed that there is the possibility of skyrmion lattice formation was this one in 2006. And the idea was that you just construct a suitable Ginzburg-Landau free energy functional, and you can show that in such a functional states which have these skyrmion textures are the ground states. Then, more recently there have been efforts to connect these free energy functionals to lattice models, and I think this is probably the first paper which tries to do that. That you start with a specific lattice model that we are used to in strongly correlated systems, and then you basically, starting from this elementary electronic model, one tries to bring out the form of this free energy functional and argue why such terms should exist. And it is shown in this paper that if you have Rashba type spin orbit coupling, then you can actually derive many of these terms, and then it sort of validates the existence of such a free energy functional. The second class of efforts for this understanding is what I can call lattice models. So here one studies explicitly models of spins on lattices, and these are again further in different categories. So you can have lattice models involving just classical spins, and some examples are given here. You can have quantum spin models, which one of the examples is discussed in this paper. And then you can also have models which involve itinerant electrons explicitly together with the magnetic moment, and this is sort of Hund's rule type or Kondo lattice model type models, and some recent papers have been kind of coming up in this. And our effort has been essentially to look at models in this class and ask the question as to which of these skyrmion type textures are possibly understandable within these models. And so with that, let me sort of come to now our work. So here is the Hamiltonian that we consider. So you have a kinetic energy, electronic kinetic energy term described by this, and it is coupled to classical spins. Well, right away I say that we will assume these spins to be classical. And so the description of the kinetic energy or this model basically is that you have this electronic spin which can move around over over the lattice, which also contains the classical spins. And of course, there is local coupling of this electron to the classical spins. Now, the next term that we have in the Hamiltonian is Rashba type spin orbit coupling, essentially a lattice version of what is written in this blue box. And if you think about this term, this is essentially a spin flip hopping term, right? So on a lattice, spin orbit coupling is nothing but a spin flip hopping. And now question is, how do we study such a model? So you have 2 degrees of freedom in this model. You have localized spins, these blue arrows, and the itinerant fermions, which are these red arrows. And notice in this model, there is no direct coupling between the localized spins. So one way to directly study this model is to implement what one calls a hybrid Monte Carlo simulations. So you have basically simulations for these classical spin variables, but the process of calculating energy for a given configuration of spin variables involves solving the corresponding fermion problem. So a fermion diagonalization is required at every step of the Monte Carlo update. Nevertheless, one can do this for small sizes, small lattice sizes, and one can get sort of numerically exact answers of what are the states in such a Hamiltonian. One can apply or implement approximations to go beyond this small size limit, because if you want to understand skyrmion formation and all, you need larger sizes. So we have done simulations using this hybrid Monte Carlo method, but that is not what I'm going to kind of focus on here. What I'm going to basically describe now is a way to arrive at an effective model for the classical local spins by integrating out electrons, and this is achieved in line with how one arrives at the double exchange model in the absence of spin orbit coupling. So just a reminder slide that if you had a model which looked like this, then you can basically do a projection of this electronic spins in directions which are either parallel or anti-parallel to the localized spin. And if the coupling with this localized spin is large, then you can essentially throw away the anti-parallel sector, and you have a Hubbard model-like situation where parallel sector and anti-parallel sector are like lower and upper Hubbard bands, and the anti-parallel sector essentially corresponds to configurations having double occupancies, right? So, given this change, what one can now do is simply look at the Hamiltonian in this parallel sector, and the consequence of this is that the hopping parameter for these new fermions, which you call d parallel and d anti-parallel, so the hopping parameters are dependent on the directions of the spins, and one can also write it effectively as a Hamiltonian for those classical spins, and this acquires a structure which looks like 1 plus s dot s. So essentially, this says that there is a ferromagnetic coupling between spins via this mechanism. There is an overall negative sign in the Hamiltonian. Now, what we can do what can be done sort of pretty straightforwardly, although it's a little bit involved in terms of algebra, is that you essentially go through the same step with the spin orbit coupling included in your model. And the consequence is that now you have basically a new hopping, which you can call a Gij, and it is also dependent on the direction on the lattice. And this is a combination of the spin preserving hopping T and a spin flip hopping arriving from the spin orbit coupling. And so each of these guys can now be modified via the double exchange mechanism, and they become dependent on the orientations of the background classical spins. Okay, so you have a new hopping parameters and both T and lambda type, and they have different dependencies on the background spin configurations. So the details of this is given in this paper. Now it turns out that you can further simplify this and write it in a Hamiltonian form, which means that I can write a classical Hamiltonian for spin configurations where you have some coupling constants D, And these Ds are nothing but the expectation values of certain operators, which are kinetic energy like operators in the ground state. So it's a bit tricky as to how to calculate, how to arrive at this Hamiltonian. However, what is interesting to look at is the form of this Fij gamma. And the form of Fij gamma has this structure, which has essentially the normal double exchange term, which we had discussed earlier, 1 plus S dot S. And then you have new terms, which are Zelsinski-Moria-like terms, however, with a strange dependence on the direction. So the D, the corresponding Zelsinski-Moria vector, or which commonly is denoted as D vector, depends on the direction on the lattice. So if you go along a bond in the X direction, then the gamma prime is basically Z cross X, which is Y. So so that's how this is, and you can call it an anisotropic DM interaction. The last term here has firstly an antiferromagnetic sort of a part, and then you have, if you look carefully at this term, this is a Kitaev-like interaction, in the sense that you components of spins interact, single components of spin only interact along a given direction. For example, SX interacts along X direction, and SY interacts along Y direction. And so it's a combination of these terms that is present in this spin orbit modified double exchange model. So what we can do now is simulate this particular Hamiltonian. So it's, it's still not an easy Hamiltonian to kind of immediately write down ground states of. So one needs Monte Carlo simulations to again figure out what are the ground states of this Hamiltonian. And that's what we do. So we simulate this derived classical Hamiltonian, and these are the plots as a function of temperature of various components of the spin structure factor. So essentially, if you calculate the full spin structure factor, you can identify what kind of order is present in the system. So what we have looked at we have looked at actually component resolved spin structure factor and plotted different components of this as a function of temperature to identify different phases. So instead of trying to understand the phases from this picture, let me go to this one, where we have essentially summarized what happens to the spin structure factor at low temperatures. So if I look at, by the way, alpha denotes essentially the strength of spin orbit coupling. So if I look at zero spin orbit coupling, of course, we expect a ferromagnet. It's a normal double exchange model. So you start with a spin structure factor, which looks like a peak at 0, 0. And then it evolves at small alpha, it evolves into a pattern, which is like a diffuse circular ring. Okay, and if you keep increasing the alpha value, it sort of begins to form arcs around these 4 points. Then it moves on to what we call a single Q state, a simple spiral state. And then it moves into a multi-Q state, a simultaneous presence of these 4 peaks. And finally, this multi-Q state sort of continues and reaches the edges of the Brillouin zone. And if you essentially, this particular evolution of the spin structure factor can also be tracked in terms of the change in the magnitude of the modulus of Q vector as a function of the spin orbit coupling strength. So you start with a ferromagnet, and then the magnitude of the Q vector is changing continuously, except there are some plateaus which correspond to some extra stable phases like this. And in terms of phase diagram, this can be summarized as a ferromagnetic phase, and well, this phase we term this as a classical spin liquid, because essentially there is a diffuse ring pattern in the spin structure factor, and there is no specific order. Then one moves into a single Q state, a Skyrmion crystal, and a variant of that. And if you look at the real space images of all of this, it basically looks like this. So a ferromagnet we have not shown, it's a trivial one. So the real space images of this diffuse ring pattern state appear like this, basically, with the width of these domains shrinking as you increase spin orbit coupling. And eventually these are single Q and Skyrmion crystals and their variants. I must say that the spin orbit coupling sort of beyond the right-hand side of this picture is kind of almost unphysical, in the sense that that's very large spin orbit coupling, which we probably cannot achieve in experiments. And well, so I sort of, we were intrigued specifically by these strange patterns, because when you see these things, the first doubt is that, is there some metastability issue in the simulations? We ensured that there is no metastability issue. In fact, there is a very interesting degeneracy of states that is present due to this term. It turns out that if you consider a spiral ansatz for the configurations, and then try to minimize energies for different spirals, then,
Sanjeev,
yeah.
22 minutes.
Sure, yeah, I'll try to complete in 3 minutes, yes. So the spirals moving along different directions, their plane of spiraling and the Q vector have a certain relation. And as long as that relation is satisfied, the energies of these spirals is same. So in a way, it turns out that if a spiral turns around like this, it does not really cost it much energy, as long as it turns in a way that the Q vector also continuously changes. So, so these are not artifacts of the simulations. This is what confirmed. Now, the next question is, what happens if you apply magnetic field to these? Okay, so, and this I will simply show in terms of this simulation of it runs. So if you start with one of these spiral pattern kind of a picture and increase Zeeman field, this is what you see. So these filaments break into skyrmions, and eventually with increasing magnetic field, the skyrmions go away as you approach a fully saturated state. And this is summary sort of this field dependence. So we arrive at this interesting looking phase diagram where you have sparse skyrmion phases which look like this, or packed skyrmion phases which look essentially like this, and which have the corresponding spin structure factor having this hexagonal peak structure, and so on. So, well, in some sense, the main story that I wanted to tell is complete, and I can simply in the remaining time ask a few questions and just quickly answer them. So the first question is, what if the spin-orbit coupling is of Dresselhaus type? So we have addressed this question in this paper, and it's pretty simple in the sense that only thing that will change is that the nature of these pattern formation will change, because the symmetry of the underlying spin-orbit coupling changes. So you can derive the corresponding spin model again, and it turns out that instead of skyrmions, you will get anti-skyrmions now. Now, the question is, Rashba coupling generates for us nail skyrmions, and Dresselhaus coupling generates anti-skyrmions. So is it possible to understand block skyrmions within this framework? And it turns out, once again, this effective Hamiltonian gives a very simple clue about it. So if you look at this term, T into lambda appears in this term, and it turns out that if you can change the sign of this term along one of the directions, so gamma cap denotes X or Y. So if you can change the sign of this term along one of the directions, you would achieve block skyrmions. And it is actually possible to essentially write down these spin transformations. So one doesn't have to do this simulation again and again. You simply analyze the sign of this term, and appropriate transformation can be made in the spin configurations without any change in energy. Okay, so it's actually interesting that with some change in relative sign of the hopping parameters along X and Y direction, one can achieve from anti-skyrmions block skyrmions. So the rest of the part of the story, I think I can skip. This is basically about what happens if you have insulating phase. And so I'll skip this and just go to the conclusions and maybe take up questions. So here is my conclusion slide. So what we have shown with the help of this model Hamiltonian study is, first of all, a simple understanding of how different kind of skyrmion, anti-skyrmion patterns can form with the combination of Rashba and Dresselhaus couplings and the relative sign of the hopping parameters along X and Y direction. And the other interesting result of the study is that we have found these filament-like structures in the zero field states are not any artifact of defects or anything. They are actually, they represent the genuine physics of this strange anisotropic Zelsinski-Moria coupling. And as you apply magnetic field on these, one achieves a skyrmion crystal state. And this is, extremely consistent with what is seen in some experiments. And so with this, I can stop, and thank you for listening.
Okay, thanks, Sanjeev, for a very nice talk. So we are open for questions here. So anybody who wants to ask anything, you just unmute yourself and post the question. Okay, doesn't look like we have a question. So, okay, so the talk was probably exceptionally clear. So we'll just move on probably then. And one can always ask question to the speaker in the breakout room later. I mean, that's not a problem.
Sure.
So,
thank you, Krishna.
Sanjeev, could you please unshare?
Sure, sure.
Yeah, thank you. Okay, so the next talk is by Yasir. Okay, Yasir, do share and okay, so the next talk is by Professor Yasir Iqbal from Indian Institute of Technology, Madras, and his title is Spin Liquid Physics on the Square Kagome Lattice. So Yasir, okay, go ahead. I'll give you a heads up at 22 minutes.
Yeah, thank you. Good morning. Yeah, thanks, Krishnendu.
Good morning.
So I would like to thank the organizers for inviting me and giving the opportunity to talk about some of our very recent work on exploring spin liquid physics on the square Kagome lattice. In general, I mean, the search for quantum spin liquids, has focused on 2 dimensions, and there people have mostly looked at the Kagome lattice geometry. And the special thing about that is actually it's a corner sharing arrangement of triangles, which leads to an extensive degeneracy of classical ground states, which might not be lifted by quantum fluctuations, and thereby giving rise to some kind of exotic non-magnetic phases. In this work, I'm going to look at a much less explored version of the Kagome lattice in some sense, which is called the square Kagome lattice. And the work is motivated by this paper that appeared a year ago in Nature.com by the Japanese experimental group, exploring and trying to argue that there is some kind of a spin liquid phase, possibly a gapless spin liquid that arises in this geometry, and this material is the first of a kind realization of this geometry, which has hardly been explored theoretically. So here also you see that it's an arrangement of squares which have these shurikens, coming out from each side, and it forms a corner sharing arrangement of triangles. And in particular, this lattice is actually a non-Archimedean variant of the Kagome lattice. And what this means is that there are actually topologically 2 distinct set of sites, the ones that form on the square and the ones on the triangles, and they are crystallographically inequivalent. And it therefore features 2 symmetry inequivalent types of nearest neighbor couplings, the ones on the triangle bonds and the one on the square bonds. And so the work we'll do is a theoretical investigation motivated by this, trying to understand the microscopic origin of the spin liquid on this lattice. So a brief recap, I mean, if we treat a system of interacting magnetic moments, which are, let's say, frozen in space, then a very good description at low temperatures is given by this Heisenberg Hamiltonian. And we know that in spin mean field theory, the ordering temperature or the Néel temperature for this antiferromagnetic model is basically given by the standard expression, which scales with the coordination number and the spin length and the exchange interactions. And the idea is that, is there a possibility that in some scenario where you're able to suppress this temperature down to, say, ideally 0, such that the system does not, evades any kind of long-range magnetic ordering? And the simplest way one can do it is that if you have a classical ground state and the spin value becomes finite, then of course this is no longer an exact eigenstate of the exchange Hamiltonian, because it is dressed by fluctuations with different number of spin flips. And in one dimension, we know, for example, there is no long-range magnetic order because 0-point oscillations are so strong that they wipe out any kind of long-range order. But in 2 dimensions, since order is permissible, the idea is that we need to add some little extra ingredient, and that is what is called as frustration, which could be parametric in origin. For example, if you take a square lattice with the nearest neighbor antiferromagnetic interaction, and you introduce, say, for example, diagonal couplings J2, then they clearly destroy or try to frustrate this nail order. And the other is of geometrical origin, that if your building block or your the elementary motifs have odd number of sites, then that clearly leads to a confusion in the spins, and they don't know where to order. For example, this is typically for the antiferromagnetic easing model I've shown you. So quantum fluctuations, when they combined with small values of spin, low coordination number of a lattice, low dimensionality, could possibly lead to a scenario where you evade magnetic ordering down to 0 temperature, and this is what you call as a quantum spin liquid. So the way to imagine this is that, I mean, if you take just 2 isolated spins, then we know quantum mechanically its ground state is a antisymmetric combination, the singlet. And since the overall state that we want to describe is non-magnetic, the Lego building block of this is basically a singlet. And this was Anderson's idea to construct his non-magnetic states using singlets by considering a massive superposition of singlet coverings, which are resonating and thereby lead to a lowering of energy in second order perturbation theory. And this gives rise to the schematic illustration of an RVB state, which does not break any spatial symmetry and therefore does not have any local physical order parameter, and could possibly feature fractionalization in case the spin liquid has gapped excitations. The other possibility of a non-magnetic phase is to have valence bond solids, which break some kind of they definitely break translational symmetry, but they could also break some point group symmetries. And here it's a schematic illustration of a dimerized phase in the square lattice, which could also be of the plaquette type and so on and so forth. But these phases break some point group and translations. So now coming back to the material, this material has come into limelight because it's you can approximate it very well in terms of isolated 2-dimensional layers of square kagome, where you see that there is actually non-magnetic atoms which occupy these interlayer spaces among these between the different magnetic layers formed by the copper 2+ ions, which are the square kagome layers. So you have basically one set of sites located in one plane, and then it's sort of sandwiching the other set of sites. And due to this difference in this valence numbers between these non-magnetic ions and the copper 2+ magnetic ions, this kind of system avoids any kind of site intermixing, just like what is the problematic issue in Herbert-Smithite, which was a celebrated material to realize the 2D kagome physics. And the other thing is that due to the presence of these large non-magnetic ions, the interlayer spacing elongates along this direction, and this leads to a highly 2-dimensional character for this system. And the triangles here in this case are scalene triangles, and they feature different, the copper, oxygen, copper super exchange path, which leads to a different, exchange interactions. So the reason why this system is so, nice is because of the crystal perfectness and the high 2-dimensionality of this. So this is good for studying the intrinsic magnetism of the kagome, the square kagome layers. So they have performed magnetic and thermodynamic measurements, which reveal a pretty large Curie-wise temperature and negative, pointing to antiferromagnetically, a frustrated system. And the Curie constant is consistent with effective spin 1/2 moments for copper 2+ ions. They also carried out magnetization measurements, which indicate that the number of paramagnetic free spins is rather a small percentage of the total copper spins. And also, strong antiferromagnetic interactions were pointed out, and the specific heat behavior, although features a small Schottky-like anomaly, but that only, I think, has been argued to be due to development some short-range spin correlations. So it seems that long-range magnetic and VBC orderings are not observed in the susceptibility, magnetization, and specific heat measurements. And also convincing evidence of strongly fluctuating copper 2+ spin moments down to the lowest temperatures around 58 millikelvin is given by muon spin relaxation data, which show a long time, the decay of the muon, the weak low longitudinal field signal down to pretty large times around 15, microseconds. And then also they did inelastic, neutron scattering, which shows these streaks of excitations at around 0.8 or so angstrom inverse, whose intensity continuously increases with decreasing energy down to the elastic line. And there was no observation of any kind of a spin gap down to the instrument resolution. So these are plots done for various, incident neutron energies. So it seems that all in all, the picture is consistent with some kind of a spin liquid, possibly a gapless spin liquid or one with a small gap and a continuum of spin-on excitations. So now comes that, what do theory and models say? So as I said, very few studies have been done on this model. Many years ago, there were some small-scale exact diagonalization studies. But as we all know, that the issue with these is that it's difficult to to extract any physics on the behavior in the thermodynamic limit. And more recently, there have been some Schwinger boson mean field studies and some quantum dimer model studies done by the Dresden group and also in Grenoble. But they all give very conflicting, ideas on the possible ground states. Either it's like a topological nematic spin liquid, nematic in the sense of breaking spatial symmetries, or some kind of dimerized state. There have also been claims of spin liquids. So it's not at all clear what the nature of the ground state in the thermodynamic limit is, and it remains elusive. So what we did was to start from the simplest model of an isotropic Heisenberg Hamiltonian defined in the shuriken lattice, and use a combination of state-of-the-art numerical quantum many-body methods like variational Monte Carlo, multivariable variational Monte Carlo, which does not assume any kind of ansatz, and flavors of functional renormalization group. And this appeared in this archive preprint with this collaboration. And this is currently in print to appear in PRB letters. So I'm going to describe basically our efforts from the variational Monte Carlo point of view, where this is a method which has been quite successful for 2D describing models with 2D quantum spin liquids. And we know, as I said, exact diagonalization has always this issue with small system sizes, and slave particle mean field theories, have difficulty in terms of enforcing the constraint of 1 fermion per site. And the good thing about Monte Carlo is that you can go beyond these fermionic mean field theories by including some part of quantum fluctuations arising by imposing the constraint of 1 fermion per site. So the idea is simply that you have to devise a variational ansatz. You can then calculate, optimize the state by optimizing some kind of, the variational parameters, and calculate any desired expectation value by drawing samples from the standard Metropolis algorithm. So different types of states can be described. I mean, you can describe the usual classically magnetically ordered states by starting from a classical state and including, fluctuations via the Jastrow term. And then one can also have a versatile framework to capture spin liquids and valence bond solids. So the way we do for, including magnetic order is to define some classical magnetic order in the XY plane parameterized by a pitch vector. For example, this kind of Néel order. And then you basically, act on it by the Jastrow factor, which introduces transverse fluctuation. So it's basically like doing spin waves, but it goes beyond the standard linear spin wave theory. This is essentially what you do in Holstein-Primakov. But then you can also describe non-classical states like spin liquids and valence bond solids, which have no classical counterpart, but you need something different. And the way you do it is to go from the language of spins to the language of fermions by going into the SU2 Abrikosov pseudo-fermion representation, where you express the spin operator at every site as a bilinear between the fermions, these are basically some spin 1/2 spin-on operators. And this is the standard Pauli matrix. The issue with going into the fermion language is that although you preserve the spin algebra, the Hilbert space gets enlarged to include these unphysical states of doubly occupied and empty sites, which must be removed. And fortunately, this can be done exactly in Monte Carlo sampling. And therefore, the variational Monte Carlo framework exactly imposes the constraint and gives you a legitimate wave function residing in the correct Hilbert space. The other thing that happens that when you rewrite the spins in terms of fermions, you introduce an extra symmetry in the problem, is that the most general transformation you can do to the fermion tuplet, which keeps the physical spin operator invariant, is an SU2 transformation. And therefore, besides the time reversal and the lattice symmetry of the original Hamiltonian, you now have a symmetry which acts internally inside the spin operator, and therefore becomes a gate symmetry for the original Heisenberg model. And it is this extra symmetry which then allows you to distinguish different kinds of spin liquids within the framework of projective symmetry groups. So the idea now is to define some auxiliary BCS Hamiltonian, which consists of spin independent hopping and some singlet pairing. And from this, by diagonalizing it, you can define a BCS ground state with some pairing amplitudes. And schematically, the state can be expanded as this kind of a superposition, and which also includes some unphysical states which you have to remove by enforcing this Gutzwiller projection Gutzwiller projection operator, which kills these empty and doubly occupied sites. So this numerical implementation, as I said, is very simple. You just diagonalize this quadratic Hamiltonian. You get a Slater determinant. You fill up the single particle orbitals, and then when you do the numerical, the Monte Carlo sampling, you basically can eliminate and not go over any states which have unphysical configurations. So the nice thing, as I said, is that this Gutzwiller projection can be done exactly numerically exactly in this Monte Carlo sampling, and therefore one lands up with a bona fide wave function. So these hoppings and the pairings constitute the variational parameters of the problem, and you can generalize the state by also including the possibility of having a long-range magnetic order by adding a fictitious local Zeeman magnetic field and then treating it as an optimal parameter. If it goes to 0, you land up with a non-magnetic state. If it remains finite in the thermodynamic limit, that indicates your system has long-range magnetic order. And then you can also introduce modulations in these hopping and pairing patterns, which break symmetries according to a certain pattern of strong and weak bonds, and you can study various potential instabilities to dimerization. We also employed this many variable VMC, which basically does not assume any kind of ansatz for this quadratic Hamiltonian, but just goes like in a brute force way and performs an unconstrained optimization of all the BCS pairing amplitudes. The cost you have to pay is that you land up with a very large number of variational parameters which scale as n squared, and therefore you are restricted in the system size that you can go to, and also have the issue with to get stuck in some kind of a local minima. So now I begin describing the new results in our work. So what we did first was to do a projective symmetry group classification of all possible quadratic Hamiltonians with a U1 low energy gauge group on the square Kagome lattice. And we found that there are 4 and only 4 fully symmetric spin liquids, which can be characterized by a flux triad. So this is basically the flux that the spin-ons experience when they hop around different plaquettes. So you have the standard state with the 0 flux through all plaquettes, which is the uniform RVB state with a spin-on Fermi surface. You have a state which has say a pi flux. So these dashed lines denote a negative sign for the hopping. Pi flux through the square. This is a Dirac spin liquid, and then you have 2 different other kinds of spin liquids with different patterns of flux distributions. And then we also classified chiral spin liquids, which have fluxes different from 0 and pi. So there's like a pi half flux, for example, threading through the odd-sided plaquettes, which breaks time reversal symmetry, together with parity, but preserving their product. And we had also some staggered flux spin liquids, which break time reversal and break rotation symmetry, but preserve their product. And therefore, and the idea was to study their competition of spin liquid with some kind of valence bond crystals, which had previously been proposed from quantum dimer models, which go beyond the nearest neighbor basis. For example, in this paper by Ralko and Russo-Chatzakis, and the Dresden group of Russo-Chatzakis, Goderish, Meusner, and Van der Brink, which proposed that the ground state is some kind of either a pinwheel valence bond crystal or a loop 6 VBC in terms of its resonance pattern, and breaking the translation symmetry modulo 2. So before I go into the quantum problem, I want to describe some similarity with the Kagome lattice as regards its classical spin states. So when you are dealing with this ideal model where the coupling on the triangular bonds is the same as the square bonds, you actually have an extensive accidental degeneracy of ground states of the 120-degree type, where on every triangle you must satisfy this constraint that the sum of the vector spins must be go to 0, and therefore the simplest way to do it is to have a relative angle of 120 degrees here. And either you have a translationally invariant version of this order, which we dub Q equals 0, or you have one with an enlarged unit cell called square root by square root 3, in line with the the Kagome terminology. And as we know that whenever you have these kind of extensive degeneracies, they give rise to a flat band, and dipolar correlations in real space, which when Fourier transform, give rise to this beautiful pattern of pinch points or non-analyticities in the structure factor and these bow ties. So this is what you see also in a large N plot here. So in the case of spin 1/2, we first showed that there is absence of long-range, dipolar long-range magnetic order by doing a size scaling of the local Zeeman field in 1 over the system size, and you see that it goes to 0 in the thermodynamic limit. And we could also compute the magnetization directly from the expectation value of the, the spin-spin correlation function, and we see it dies to 0 in the thermodynamic limit relatively quickly with increasing system size. Also in the pseudo-fermion FRG, the susceptibility tracked at the ordering wave vectors for these two orders monotonically increases as the effective temperature or the RG cutoff goes to 0 and not shows any kind of a breakdown. So after having established that there is no long-range magnetic order in the system, we went on to study the energetics of the spin liquid states, both at the cell-consistent mean field level and after performing the Gutzwiller projection. So these are the different fully symmetric states with different fluxes I showed here. These are the chiral states and some dimer states. And we see among the spin liquid states at the mean field level, one of the chiral spin liquids is actually the lowest energy, which is consistent with the Roxar rules. The Roxar rules simply dictate at the mean field level what is the optimal, the flux configuration by minimizing the energies of isolated plaquettes. And this is consistent with that. However, the dimer states tend to have a lower energy, and these dimer states arise as an instability of the Dirac spin liquid, basically on this lattice. And the hierarchy is such that the states with loop 6 resonances tend to have the lowest energy. However, once you perform a Gutzwiller projection, there are two features. Among the spin liquid category, the chiral spin liquid no longer remains, the lowest energy state, which is in fact given by a spin-on Fermi surface state with 0 flux. But then, if you actually look at the two dimer states treated as an instability of the Dirac spin liquid, they actually tend to have the lowest energies, and among which the hierarchy actually gets inverted. It's the pinwheel VBC which breaks, the mirror symmetries, which tends to have the lowest energy. So this pinwheel VBC is 8-fold degenerate. Factor 4 coming from translations and a factor 2 coming from the two pinwheel orientations that are possible. So the first sort of idea we get is that the ground state is not a spin liquid. It's dimerized, but it's not dimerized in the form that has been predicted from either quantum dimer models, which even go beyond the nearest neighbor basis, valence bond basis. So this is something new. And so what we did was to start from different spin liquids ansatz and impose this pattern of symmetry breaking. And here I show you the energy optimization versus Monte Carlo steps by starting from a Dirac spin liquid.
Roughly 22 minutes.
Okay, thanks. Yeah, I'll wind up very soon. So yeah, so you impose this on a Dirac spin liquid, you impose this pattern of dimerization, and you see that a pinwheel VBC actually goes to a lower energy solution compared to loop 6. We also verified this by starting from, without assuming any form of the variational ansatz and doing a brute force or an unconstrained optimization of the BCS pairing function, and then measuring dimer-dimer correlations, which again show this pattern of pinwheels and a breaking of translational symmetry along the two directions here. So the picture we get from MBMC was also, as I said, of the pinwheel VBC was also corroborated by actually doing a size scaling of the eigenvalues of the susceptibility, corresponding to the symmetry breaking patterns with the various irreps of the C4b point group. So here the pinwheel pattern is basically corresponds to the A1 irrep, and we see that the susceptibility is actually the largest in the thermodynamic limit, whereas for the loop 6 VBC, which corresponds to the B1 irrep in the usual Landau notation, it dies out. So this contradicts the picture that has been proposed, as I said, from either mean field theory or from dimer models. Finally, we computed the spin structure factors from both these approaches, which show, this is the first Brillouin zone, the rotated and the large extended, Brillouin zone shown by the dashed line, where you see a diffuse pattern of distribution of intensity along the Brillouin zone boundary. Indicating some kind of a non-magnetic state, and the agreement between an unbiased MVMC and a VMC with ansatz seems to be rather good, where the dominant soft maxima are correctly captured. They seem to be located actually at the pinch points where the original pinch points were. We also did a projected entangled pair study, IPEP study, which again confirms energetically that our our energies in the thermodynamic limit are in good agreement with the energetics from IPEPs as well as the picture it presents. So all in all, the conclusion is that it seems that the nearest neighbor spin 1/2 isotropic model features a dimerized capped ground state, which is very different from the picture that has been proposed from existing, studies. But it also points to the fact that this is not an adequate description of the material, which would either involve, anisotropic nearest neighbor couplings. So because the couplings on the triangle and the square we assume to be the same, so you might have to relax that constraint, which is not symmetry dictated, or feature further neighbor interactions. But what I suspect is that the role of Zaleshinsky-Moria interactions cannot be discounted for. And further work is on in our group to actually, collaborate with some people doing ab initio calculations and also to map out the larger phase diagram, which indeed at the classical zero temperature level from Latinger-Tisha features a large region of extensively degenerate ground state manifold, which is dubbed as the classical spin liquid, and to see what is the corresponding spin 1/2 quantum phase diagram and try to place the material. What we did right now was sitting at a 1,1 position, which is dimerized, but it seems that it's a pretty large space and there could be regions of either gapless quantum spin liquid or other exotic phases lurking around. So with this, I come to the end of my talk, and I'll be happy to take questions.
Okay, thank you, Yasir. A very nice talk. So we are open for questions now. So please unmute yourself and just ask if you have a question.
Okay. Yeah, thanks for the nice talk. So yeah, I mean, maybe you mentioned, but I didn't somehow follow. So how your theoretical kind of expectation matches with the experimental data that you showed in the beginning?
Okay, so
for that particular compound.
Right, for that particular compound, what we compared with was to look at the location of the powder averaged, peak in the structure factor, which is given here, where they integrate the neutron data over a certain energy range, and the peak seems to lie at around 0.8 angstrom inverse. And what we get is something, the value which is larger than 1. Okay, so it seems clear that basically the nearest neighbor isotropic description of is not adequate, and one must take into account either Zaleshinsky-Moria interactions, which at the classical level will shift the peak to a smaller value, or further neighbor interactions. And our work is going on to actually compute the dynamical spin structure factor for this extended model and try to see whether we get the peak at roughly the correct position, and then and try to identify the nature of the phase. So yes.
So your model also is telling that it is indeed a gapless spin liquid, but maybe.
No, it's not. It is dimerized, it's capped, and that's what I'm saying. It's inadequate description. A nearest neighbor description is inadequate for the material. We need to take into account further neighbor couplings, possibly to stabilize a gapless spin liquid. We do not find a gapless spin liquid for the spin 1/2 isotropic model. So some more work is necessary, which is ongoing. Yes, it seems that the material lies somewhere else in this phase diagram, not at the nearest neighbor point. And there we don't know what happens with spin 1/2. We only know the classical phase diagram from this work.
Okay. So somewhere you probably showed the susceptibility. Sorry. May I?
Yeah, right.
Go ahead. Sorry.
So you showed somewhere susceptibility as a function of temperature, right? Or am I mistaken?
Yeah, so I showed you the RG plot of the static susceptibility, the zero frequency component, as a function of the RG cutoff, which can, in a very loose sense, be treated like a temperature scale. Yes.
So I mean, is there any kind of why this low temperature upturn? Do you have any idea about it?
This is difficult to resolve. I mean, this could be an artifact of the frequency discretization of the vertex functions, actually. So one needs to actually look. So I'll be happy to discuss this with you. But this typically arises because you discretize the frequency dependencies of your vertex functions in some in some discrete scale on a linear logarithmic scale, and these features at very low temperatures could most likely be an artifact of that.
Okay. So Yasir
Thank
and
you.
Mohit, maybe you guys could move into a breakout room
Sure,
if you
sure, sure,
have this
Sure,
thing.
sure. Okay. Thank you.
So
sure, definitely. Yeah,
unless
thanks.
there are other questions, let me just okay. Let's just move on to the next talk.
Okay, thank you.
So, Abhishek, would you please share your?
Yeah.
Just share the talk.
Just a second, yeah. Yeah. So can you see my screen?
Yes. Okay, perfect. Okay, so the next talk is by Dr. Abhishek Samanta, who is now in Technion, and he's going to sort of talk about Hall coefficient of multiband models. So Abhishek, since this is a 15-minute talk, I'm going to give you a heads up at around 12. Is that okay?
Okay, yeah, sure.
Yeah. Sure.
Okay. Good morning, everyone. I am Abhishek Samanta. I am a postdoc at the Physics Department of Technion, Israel Institute of Technology. I am going to talk about one of my recent works. So the title of my talk is Hall coefficient of multi-band models. So his work has been done in collaboration with Ashirbad and Daniel Arovas. Let me begin with a very brief introduction to the Hall effect and Drude theory for charges. We know that the Hall effect arises from the basic fact that the magnetic field causes the charged particles to move in circles. Now, the frequency with which the charged particles go around these circles is fixed, and they are given by so-called cyclotron frequency, omega c equals to EB over MC. Now, Drude theory assumes two more ingredients into this picture. First one is an electric field, and the second ingredient is a linear friction term, which comes with a scattering time tau. So the equation of motion for the electrons is given by this. This is known as the Drude model. Now we are interested in the equilibrium solution of this equation, which have dv dt equals to 0. So setting dv dt equals to 0 in this equation, we see that the velocity of the particles must obey this following equation. Now, using the relation j equals to nev, we can convert this equation in a matrix form, and now we can invert this matrix equation, and comparing this with the standard Ohm's law, j equals to sigma e, we can find the conductivity sigma. Now, notice here that unlike the usual Ohm's law, here the conductivity is a tensor, which has off-diagonal terms also. In fact, the off-diagonal terms are mainly responsible for the Hall effect, which we call sigma h. So now we will discuss the limiting case where the scattering time is small. That means when omega c tau is much smaller than 1. So this is the case for most of the metals at any reasonable field. In this limit, we can ignore the omega c tau square term in the denominator, and the longitudinal and transverse conductivity can be simplified like this. Now we will calculate the Hall coefficient. So in general, we will take the reasonable assumption for the metals that sigma xx has a limiting value at 0 magnetic field, and sigma xy on the other hand, by symmetry, is an odd function of B. So the zero field Hall coefficient is defined as the derivative of the transverse resistivity rho xy with respect to the magnetic field, and in the limit magnetic field going to 0. So now this can be rewritten in terms of conductivity like this. Now, if one inserts the value of sigma xx and sigma xy from above, one can easily see that the effective mass gets cancelled out, the scattering time also gets cancelled out, and one is simply left with 1 over density, which means that RH becomes 1 over NEC. So this is an equilibrium quantity, but we are talking about transport. So the question is, how can an equilibrium thermodynamic average describe something which depends on currents and scatterings and so on? So this is like a miracle which happens I mean, at least for the Drude theory. So the question is this true in general, or this is only valid for the Drude theory? Now, beyond the Drude theory, there is of course the band theory, and band theory has strong potentials, but they are lumped into the band structure. And Boltzmann theory applies to the band theory. But this again gives rise to the same miracle that when we calculate the Hall coefficient, it just measures some static equilibrium quantity which is related to the Fermi surface shape. For instance, here we have plotted the Hall coefficient as a function of density for a tight binding model in two dimensions, and we see that at small density, small carrier density, so the Hall coefficient diverges like 1/n, but near the half filling, there is a zero crossing. So now there are many materials where the Boltzmann theory do not work, like they are called the bad metals or strange metals like this. For example, in some material, the DC resistivity exceeds the so-called Ioffe-Regel limit, and so on. Now, if one translates these materials into the Drude-like picture, the mean free path becomes so short that they cannot be described by the independent quasi-particles. And hence, they cannot be studied using the Boltzmann theory to calculate the transport or conductivities. So here comes the Kubo formula. However, calculating DC conductivities by Kubo formula is not very easy, because there are several limits one needs to take very carefully. For example, first one needs to take the thermodynamic limit, followed by Q going to 0 and epsilon going to 0. And finally, one needs to take the dynamics going to 0 to get the correct DC limit. There are, of course, other methods to calculate the DC conductivities. For example, the perturbation theory. But perturbation theory needs resummation of many diagrams, particularly in the limit of strong disorder and strong interaction. There are also quantum Monte Carlo, but imaginary time quantum Monte Carlo suffers from the problem of analytic continuation, and also this is limited by the frequency being always greater than the temperature. Now, in the high temperature and frequency expansion also, one needs to expand in terms of these operators, which is not very easy. And there is no well-defined DC limit also. On top of that, calculation of Hall coefficient is doubly challenging, because there one needs to calculate both sigma xx and sigma xy by the Kubo formula. So we have seen that the calculation of Hall coefficient is possible from the Kubo formula, but this is very challenging. So the question is there a way to avoid these difficulties? And the answer is fortunately yes. There is a recently derived formula for the calculation of Hall coefficient, which I will discuss now. So we will work in a Hilbert space of operators, which is called the hyperspace. Now here the Kubo formula is written in terms of the usual matrix elements of between the current operators, delta functions, and so on. But this can be also rewritten in a more formal and compact way as the matrix element of the inverse of Liouvelian in this operator space. So the question is, what is Liouvelian? The Liouvelian is a hyper operator in this space, which acts on any operator and which basically gives a an operator which is commutator of Hamiltonian with that operator. So the longitudinal and transverse conductivity can be written as the matrix element of the inverse of Liouvelian in this hyperspace. Note that all of these terms like this current Jx, 1/L, and so on, they depend on magnetic field, and it is now very convenient to take the derivative with respect to the magnetic field, which we need to calculate the Hall coefficient. So, and then after a lot of manipulation, like many terms will go to 0 in the limit of magnetic field going to 0, and we will finally end up with an expression which is in terms of the current and inverse of Liouvelian and so on. But the important thing is that it turns out that this expression is sigma squared times something, and that something must be the Hall coefficient. So we have seen a formula for the Hall coefficient, which does not involve any dynamics or a dissipative mechanism. All of them go into this sigma xx square, which will eventually get cancelled out while calculating the Hall coefficient. So this is like a generalization of the fact that tau square gets cancelled out in the Drude's formula. So now, so here is the final form of the formula which I will use. The formula is separated into two parts. So the one part is important, which is called the RH0, and the another part, which is the correction term, which also needs to be calculated. But we'll see that in many cases, they are simply small. Now, the correction terms are, of course, have infinite sums, but all of the terms here, they are written in terms of the equilibrium coefficients, and they can be computed one by one. And in many cases, they just decay fast. So the conclusion from here is that, so we have seen a formula which is applicable to general interacting and disordered Hamiltonians. The coefficients in this formula are amenable to well-controlled numerical algorithms like high temperature series expansion, variational wave functions, quantum Monte Carlo, and so on. And most importantly, all the terms involving in this equation are computable equilibrium coefficients, which I will show. So now we will apply the formula for simple cases. So the current and magnetization operators are given by this. Now first we will calculate the RH0 using them, and we end up an expression like this. So here F is related to the Fermi surface curvature, and mu0 is the conductivity sum rule, which is basically the current correlator. So first we will apply this formula to a single parabolic band given by this, and we will immediately get 1 over NEC, which is the same with Drude answer. Next, we will calculate the tight binding model case with nearest neighbor interaction, nearest neighbor hopping. So we can calculate this from this formula, and here I have plotted the Hall coefficient as a function of density.
So Abhishek, you have, it's 12 minutes, so maybe you can wrap in a couple and then take 1 minute of questions.
So here I am getting the same answer from the Boltzmann one, that okay. So now having set up the formula for the Hall coefficient, we will now use it for the multi-band models. So here the Drude theory breaks down to multi-band due to the multi-band effects and intriguing Fermi surface topology. Also, the multi-band conductivity calculations are very challenging because it involves coupled Boltzmann equations with various interband collision integrals. Now there have been some attempts from the calculation of the Hall coefficient starting from the Boltzmann theory, and for this two-dimensional whole system, it has been shown that using the Boltzmann theory, one can get a correction term from the Drude answer, which is which goes as the beta square, where beta is a Rasba spin orbit coupling. So now in our formalism, we consider a general two-band Hamiltonian now, and we consider a good quasi-particle regime, which is given by this. Now we will apply our formula for two different cases. First one is the intra-band case, where the disorder is much smaller than the band splitting. And then we will consider another case where the disorder is still small, but it can couple these two bands. Now in both these cases, we apply our formula first for this two-dimensional whole system, and we also get a similar correction, which is of the order of beta square. So notice that here the calculation is very simple, and we can do the whole Boltzmann theory calculation within a few lines. We can also extend our calculation for the three-dimensional conduction band, and there we get a correction from the Drude answer, which is dependent on density, but still it goes as beta square. So finally, we calculate the Hall coefficient for the nodal line semimetal. So when two bands touch each other along a curve, so they form a nodal line semimetal. We consider a nodal line of radius k0 in the kz equals to 0 plane. In 3 dimension, nodal line semimetal show a toroidal Fermi surface. Now we can use our formula to obtain the Hall coefficient, and we find that the nodal line semimetal exhibits a density independent Hall coefficient, which does not show any Drude-like divergence, but there is an abrupt change in sign. So here is a summary. So for multiband Hamiltonian calculation of zero.
Abhishek, maybe you can just put down the summary and we can take one question. We are really at 15 minutes. Yeah. Okay. Thank you. So is there any quick question? Well, if not, you can always go to the breakout room and ask later. So we'll move on to the next talk. So Abhishek, maybe you can unshare now. Okay, so the next talk is by Ashirbad Padhan from IIT Guwahati. So Ashirbad, can you please share? Ashir,
can you see my screen?
Yeah. Yes, now I can see your screen. Can you make it full screen?
Yes.
Okay. So the last talk of the session is by Ashirbad Padhan, and he's going to talk about emergence of multiple localization transitions in a one-dimensional quasi-periodic lattice. And Ashirbad, I'm going to give you a heads up at around 12. Okay.
Okay, sir.
Okay, great. So go ahead, please.
Okay, so hi everyone. I'm a research scholar from IIT Guwahati, and so before starting, let me thank all the organizers for giving me an opportunity to showcase my work on this platform. So the title of my talk is Emergence of Multiple Localization Transitions in a One-Dimensional Quasi-Periodic Lattice. So before going into the details of our work, let me take you to the history of localization physics. So it all started with the 1958 paper by Anderson, where he proposed that a strong random disorder can localize the single particle eigenstates of non-interacting particles, which are extended otherwise. So the model that describes the Anderson problem is given by this, where the second term describes the nearest neighbor hopping, and the first term is the on-site random disorder term. So in 1979, the gang of four, they proposed the scaling theory of localization, where they proved that there is no metal to insulator transition in one dimension, due to the fact that even a small random disorder can localize the eigenstates. So our focus throughout this talk is on one dimension and non-interacting system. However, in 1980, Aubry and Andre proposed a model that is known as Aubry-Andre model, where they showed that if we use a quasi-periodic lattice instead of a truly random one, then we can see localization transition even in one dimension. And the quasi-periodicity here is governed by this term beta, and the second term is the quasi-periodic disorder term, where this lambda is the strength of the disorder. So now, for an example, we take beta equal to root 5 minus 1 by 2, and we compute two quantities known as IPR and NPR using these formulas. For an extended state, IPR is 0, but NPR is finite, and for a localized state, it is just the opposite. So we plot the IPR values of all the eigenstates in the energy versus lambda plane. Then we can see that before lambda equal to 2, all of the states are extended, whereas all of them are localized after lambda equal to 2. So there is a sharp localization transition at lambda equal to 2, which can be seen by computing the average IPR and NPR values. And we can see here that there is a sharp localization transition at lambda equal to 2. However, the sharp localization transition is gone once we move away from the tight binding limit of the Aubry-Andre model. And in the continuum limit, the transition is via a critical region where both the IPR, average IPR and average NPR are finite. So we can see from the energy spectrum plot that for a range of BD, where BD is the depth of the disorder potential, both extended and localized eigenstates exist. However, once all the states become localized, there is no going back. That means all the states cannot be extended again. However, to burst this myth, the authors of this paper, they took a dimerized lattice model with two different kinds of hopping, and a staggered disorder potential, which is something like this. The strength is equal and opposite in alternative lattice sites. And for a value of T2 by T1 ratio 2.2, they computed the average IPR and NPR, and they showed two critical regions, and in between them there is a localized region. So there are two localization transitions happening here, and we can coin this as a re-entrant localization transition. And in the energy spectrum plot, we can see that some of the states inside this green circle, they are being extended again, even after all of them are localized around lambda equal to 2. Okay, so now we have now some questions in our mind that is this re-entrant phenomenon unique to this model? How and in this model we have hopping dimerization, along with that we have staggered disorder strength. So this makes this model difficult to realize in experiment. And one more thing, that we are making some constraints to the disorder term. So can we propose a model which is simple but still shows this re-entrant localization transition? And can we do that by without making any constraints to the disorder term? So let's find out the answer. So here we have considered, in our work, we have considered a one-dimensional lattice with staggered on-site potential, which gives rise to a super lattice. Then we put a disordered lattice which is incommensurate to the super lattice, thus giving rise to a quasi-periodic lattice. So here the first term and the third term, they give rise to the Aubrey-Andre model, and this is our staggered potential term. So if you can see, we are ending up with a similar situation like the previous case in the on-site term. So we expect that we will get re-entrant localization transition. So we plot a quantity eta, which is given by this, and in the lambda versus delta plane, and we obtain a rich phase diagram. So the blue region below the red region is the extended phase, whereas above it is the localized phase, and the red one is the critical phase. So for delta equal to 0, we are in the Aubrey-Andre limit, and if we go along the y direction, we can see that there is a sharp localization transition at lambda equal to 2. However, for an exemplary value of delta equal to 1.8, if we go along the y direction, we can see that we are going through the extended phase, critical phase, then localized phase, then critical, and then again localized, which can be verified by plotting the IPR values in the energy spectrum plot and with respect to the eigenstate index. So we can see that for some values of lambda, we are having some of the states being extended again, even after all of them are localized. So this confirms the existence of re-entrant localization transition. However, if we fix lambda equal to 1.5 and we go along the x direction by varying delta, then we can see that we have 3 critical regions, which is verified by plotting average IPR, average NPR, and 2 other quantities known as Shannon entropy and the gap ratio. So all of these quantities, they verify the existence of 3 critical regions, and thus giving rise to a multiple localization transition. And below lambda equal to 2, we can see that if we vary delta, we can have 4 localization transitions. So that means the number of localization transitions increases with lambda. So an eigenstate cannot be prepared in lab. That will be ridiculous. So we try to capture this re-entrant physics indirectly by a time evolution protocol. So first we consider an initial state where a single particle is localized at the central lattice site. Then using unitary time evolution, we calculate the time evolved states, and then we compute the probability density at different times using this formula. So we take lambda equal to 1.5, and we choose the delta values from this our time independent results, and the delta values are chosen from all these different phases. So we can see that for an extended state, there is a spreading of the wave packet without any interruption. But in the critical region, there is a bimodal distribution of the wave packet. So here bimodal spreading. So here a part of the wave packet spreads, but a part is localized around the central lattice site. And the localized phase, there is no spreading. So we can see from this plot that there is a re-entrant localization transition. Now we compute two other quantities known as the root mean square displacement and the survival probability. So the root mean square displacement given by this formula increases very fast in extended phase, but it increases slowly in the critical phases. But there is no increase, and it saturates even after a small time for the localized phase. And the survival probability, it is the probability to find the particle inside a small region R around the initial position. So as expected, in the extended phase, since we are starting with a localized state, it will tend to 0 in the extended phase, but it will have maximum survival probability for a critical phase, so which is 1, and it lies between the two in the critical phase. And we have plotted the saturated values of sigma and p for a time evolved state in this plot D. And we can see that these are behaving similar to the average IPR and NPR, and thus showing us the re-entrant localization transition. And in figure C, we have plotted the survival probability for different values of R. And you can see that for an extended phase, there is a linear increase in the survival probability. However, it becomes 1 around R equal to at R equal to 0, which is expected because we are in the localized phase, and there is the behavior is something between the two for the critical phase. So all these quantities, these two quantities, they verify the existence of multiple localization transitions in our model. Now, our model has been used numerous times to study localization physics. However, the model used there doesn't have the superlattice term or the staggered potential term inbuilt. That is used just to create an initial state. But since that staggered potential is an integral part, we have proposed an experimental scheme to prepare an initial state of type this. So first we consider a primary lattice and a long lattice along the x direction, which has a phase difference phi. And then we consider a normal lattice along the y direction. And we choose BP, that is the depth of the primary lattice much greater than VL, and we choose phi equal to pi by 3 so that we get our desired superlattice along the x direction. And then we load ultra cold atoms, for example spinless fermions or bosons like this, so that they occupy
Ashirbad, you have 3 more minutes.
Okay, sir. Okay. So if we load the atoms, then they occupy the deep lattice sites. So here the dark blue color represents the deep lattice sites, and the light blue color represents the shallow lattice sites. So they occupy the deep lattice sites, and then we selectively remove the particles from all the rows except the central row along the y direction. So now we put the superimpose the disordered lattice, which is incommensurate to our superlattice, and thus we are getting our lattice along with the initial state. So now this is my conclusion. So we found that we have multiple localization transitions in our model as a function of lambda up to 2 and up to 4 as a function of delta. However, all the interesting things happen below the Aubrey-Andre critical line, which is lambda equal to 2. So what can be done with this model? So we can see the effect of interaction, and we can see if there is a many-body re-entrant localization transition or not. And we can explore in higher dimensional systems that can we see the re-entrant localization transition in 2 dimensions or 3 dimensions. So, and what happens in an open quantum system, and what are the real life applications of this reentrant physics. So with this, I would like to thank everyone for your attention. Thank you.
Okay, thank you. We have time for one or two questions.
Krishnendu, can I ask one?
Yeah, Rasdeep, please go ahead. Sure. Yeah.
Yeah. So, Ashirbad,
Yes, sir.
at least in the case of non-interacting systems, the quantity that you were computing actually has an analytic answer in terms of the localization length. When you can look at our paper with Ahana Chakraborty and Pranay Gorantla, some tan hyperbolic of some localization, 1/1 localization length. So have you tried to fit? There's an exact answer for that. Have you tried to fit such a thing?
Analytically.
Yeah, because it's a non-interacting
yes.
problem. So it actually has an analytic answer for the
okay, sir.
precisely
so
the
while
quantity you are computing, which is, this is just the Green's function for diffusing out of this. Yeah.
Yes. So while preparing this manuscript, we came through with work where they have calculated our model analytically, and they have shown the existence of reentrant physics. So
no, that's not what I'm saying. I'm just saying that there is a formula for this n of t that you are trying to calculate numerically.
No, we haven't done that.
Okay, maybe you can look at that. Okay, fine.
Okay, thank you.
Okay, other questions? If not, let me thank all the speakers in this session for very nice talks, and I think I'm going to hand this over to Rasdeep now.
Yeah, thank you, Krishnendu. I will also thank all the speakers, and I'll also thank Krishnendu, Professor Krishnendu Sengupta, for chairing this session on a Saturday morning, coming to office for us.
Coming to my office, of course. Yes.
Thanks, Krishnendu, for doing it
welcome.
for us.
No problem.
Okay, so we will now close this session, but we will meet at 11:30 for the next session, and the rooms will open at around 11:20.